is do two major things in cosmology. One is to tell the expansion history of the universe, and the other is to tell the story of the formation of large-scale structure. And as we now know, in a sort of painful series of emergent phenomena and discoveries over the last 30 or 40 years, both of those behaviors are driven by two commodities that we imperfectly understand. And that is a problem, a challenge, if you like. I mean, this glass half full, half empty. I'm not quite in Greg's camp on where we stand. I don't think we understand everything at all that well, but I also think we're having a lot of fun, and I'd rather be in a state of some misunderstanding and having a good time. And I think that's where we are now. And I do think we are moving forward. So let me talk about observing galaxies. The simplest thing you can do, of course, is just count them. And so we've got very good at counting galaxies, and that's sometimes where we start, measuring their properties. Getting redshift is harder. And I want to just remind you that from an observer standpoint, there's actually very few fundamental observables of a galaxy. There is the redshift from a spectrum. There's the flux that you detect with your telescope, and then secondarily there are colors and perhaps a spectral energy distribution if you have multi-wavelength data. And then there's the angular size, and in detail that could be the morphology and some details, but basically those are three very simple things, and that is all you get. That's it. If you're just a strict observer, that's all you get. Everything else that you care about is cosmologically of importance and interest. The size, the physical size, the energy emitted per second, the mass, revolve around knowing a distance, and that relates to redshift through a cosmological model. So these are secondary interpreted quantities, and that's everything that really counts, actually. The observables are quite simple. And most of those observables, the simplest ones, as was known a long time ago, are poor distance indicators. These two graphs show that very simply at a redshift of 1, galaxies have an order of magnitude variation in angular size, and the luminosity function is broad, so they have several orders of magnitude of apparent brightness. So these are not good distance indicators. You have to find something with extra astrophysics to use them to create what we now call a Hubble diagram. And there's a lot of work involved in that. But as I say, we've got the sensitivity of our instruments, our cameras especially in space, are extraordinary. Here's the ultra deep field from the Hubble Space Telescope. You've all seen it, I'm sure. It's worth remembering, those of you in the audience not astronomers, that this small field, which you can't really represent except in a darkened room on a huge wall, which contains over 3,000 galaxies, is smaller than the head of a pin held at arm's length. It's an extraordinary galactic content of a tiny little fraction of the angular sky. And because we've worked through the Hubble Deep Field, because we've made measurements down to magnitudes of 30, 31st magnitude, and because we've measured redshifts for a substantial number with great work and large telescopes and months of observing time, we can say several things about this stellar content, this galactic content of the universe, accepting that this is a fair sample. And that assumption, of course, part of the cosmological principle, has been checked. We don't want to hang everything on the head of a pin held at arm's length. But in this field, given the redshifts available, we've observed, and the cosmological model, we've observed through 90% of the volume, and we've observed down almost to the level of dwarf galaxies, analogs of the Magellanic Clouds. And that means that's all there is. If you had a much bigger Hubble Space Telescope, you wouldn't see much more. It's been done. Some things in cosmology get done and they're done, right? It's the end of the story. You're not going to change the answer much. So that's a huge success of the last 20 years to have done that. And I give you, of course, the round numbers. You can make more or less accurate numbers as you wish, but they're the staggering numbers that deservedly belong in the popular culture as phenomenal achievements of human beings. So let's be proud of this. Let's step back enough to be proud of this as a result of our science in only a century of the technology that let us do this well. That we have projected, by a sampling method, about 100 billion galaxies in the observable universe, and the stellar content, if you will take it all the way down to dwarfs, it's maybe an order of magnitude more, but 10,000 billion stars. And since we're, just to put the little twiddle on that, since we're now fairly confident of the universality of the formation of planets around stars and beginning to get the census on that, you might well just take that number for the number of Earth-like planets in the universe. That's a thought. So galaxy redshift surveys have come a long way, and these are a sampling from just the last 2 decades in terms of the density of objects. You're looking at surveys that range from the entire sky on the right-hand edge to surveys that cover an area the size of the moon or the sun on the sky on the left-hand edge. So you have small field, deep surveys, you have wide field, shallower surveys, wedding cake type of structure, and there's far too many to itemize or discuss individually, so I'm just showing you the landscape of surveys. But the diagonal lines give you the number of galaxies in those surveys. And it's not just that in the sum of all our catalogs are now millions of galaxy redshifts, but they're individual surveys with millions of galaxies, and putative surveys with as yet unfunded facilities that could take that up to 100 million redshifts just from a single survey. So that's progress. That's 100 years. We've done this, of course, by being able to take galaxy spectra more than one at a time. So here, a century apart, are 2 ways you can multiplex and take the advantage of multiple observations at the same time from adjunct Cannon stellar spectra, of course, in 1910. These little spectra have the disadvantage that they're not filtering the sky brightness. So when you try this method for galaxies, you run into some problems quite quickly because the dispersion applies at every pixel, and so the sky brightness is superimposed on each of the elements of light in the miniature spectrum. In a modern spectrograph, you isolate the galaxy with either a slit or a fiber in the focal plane, and then you arrange the spectra to optimally fill the surface, the real estate of your charge-coupled device. And that would be something like here, a GMOS mosaic of spectra. And so, but you're taking the multiplex advantage as it is. And since I can't, it's important to be a little hands-on. There are a lot of historians out here, so we need artifacts. So I have a couple of artifacts, 2 of which I can pass around. One of which I won't pass around, just to show that I've done this stuff. Here's a photographic plate actually from 30 years ago from the Canada, France, Hawaii telescope, and there are high redshift galaxies and high redshift quasars on this. The one I can pass around, which is actually older, but it's a reproduction. Some of you may have seen this. There's 36 square degrees from the Impey telescope with an objective prism, and each of the mini spectra are obvious when you get it in your hand and look up close. And just to make it a little competitive, there are 320 quasars in here, and about 200 of them are high enough redshift that the light you see here was from an object that was moving away faster than the speed of light when that light was emitted, which is kind of cool. So, we've had budget cuts at our university, so the cash prize I can offer for the highest redshift quasar that you might spot as you pass around is fairly modest, but do tell me if you see anything higher than redshift 3. And then that's the old era. So I am, with gray hair, I'm old enough to be on the cusp of having apprenticed at that UK Schmidt telescope and taken photographic plates. I have the glass ones in my office from the mid-70s when I was a graduate student. Into the modern era of CCDs, my artifact from 2 years ago, observing on the Magellan telescope, which I'll pass around. It's not super breakable, but be careful with it a little bit. And it's not really sharp edge, but again, be careful. This is the focal plane of a 6.5 meter telescope, and here you see the little slits etched for, indeed, a galaxy redshift survey, working down at the 23rd, 24th magnitudes. It's important to see how we do this stuff. And as you move from the, so what happened? What happened, of course, is a revolution in technology that astronomers have benefited from. But astronomers were also in on the ground floor of this revolution. It was astronomers pushing photography in handshake with Kodak Company, and it was astronomers working with Texas Instruments and RCA and the early CCD developers pushing the technology into low light level situations, low background situations that have led to the consumer revolution where they're in everyone's hands and pockets. But at the time this transition occurred, photography, is evidenced by the film you're seeing, covering 36 square degrees of sky, was maybe very sluggish, but it was rather spacious and reliable, and you could do a lot of stuff with it. At the time, at the same time that picture was taken in 1977, CCDs were emerging from labs onto telescopes, and I used them then, and God damn it, they were flaky, finicky, they were like having your Maserati. It's fine as long as you have a mechanic, too, with you all the time. And that's what you needed. Luckily, observatories have mechanics all the time, so it's okay, you can use them. So here is the only data-intensive graph I'm going to show. It's a summary, and I'm not going to talk about it in detail, just to make a couple of simple points. To give the full baseline of this, we go back to Potsdam Observatory and a rather small telescope, 0.3 meters, and Jay Shiner taking the very first spectrum of M31 Andromeda and not speculating at the time that it was an external galaxy. Slipher, of course, we've heard about, and then the gradual evolution of the number of redshifts. You notice the size of the telescopes increasing, of course, and the integration times all very long in the photographic era. The magnitudes, the depths, not very impressive. And then summarized really in these 4 lines that are in the middle segment is a multiple stage transition in technology where you move to image intensifier, intensified image tubes made by Carnegie and other institutions. And I used those too in the 70s, and they were finicky. The ones that they use on Mauna Kea then, some of them charged up to 50 or 60 kilovolts, and at high altitude, things would arc onto your hair and your hand and your face, and there were scary things to use, really scary things to use. But that was a transition technology. Then we moved into the CCD era, and then as CCDs were tiled better into focal planes and became more reliable, CCDs, as you can understand, are essentially perfect detectors now. It's within spitting distance of perfect, and you begin to fill with fibers and slits. You get this huge multiplex advantage, and so these 5 steps generically represented here are this fantastic gain in spectroscopic capability occurring really over a couple of decades. It was not an overnight thing at all. And then represented in the second last block is a set of more modern surveys, just to give you indicative numbers of the number of redshifts and the kind of telescopes and limiting magnitudes of modern surveys. And then I just picked 2 from the most recent era, representing working at the limit with the largest telescopes and the very best and most efficient spectrographs and detectors. That's a lot of progress. Well, rather in a table, let me just show the same landmarks or high water marks in this term. So I've just, again, picked out from the very beginning, I've referenced everything to that very first spectrum of M31 with a 7.5-hour exposure at Potsdam, and then taking the Hummus and Mayo and the Sandage compilation as the sort of the beginning of the modern era. And here are these transitions in technology, and then these 2 example surveys from the very recent era. And there is a remarkable thing here. The gain in depth is just the faintest galaxies observed. No surprise there. The other axis is interesting because that's the gain in spectroscopic efficiency, factoring out integration time and telescope area. That is the gain. So it's factors of about 3 billion since the first spectra were taken, entirely within the spectrographs and within the detectors and the multiplex advantage. That's a phenomenal gain. Like I said, that's scale to constant telescope area and integration time. It's amazing. And of course, what we've learned from that is maybe it's not correspondingly brilliant as the factor of 3.5 billion. We're trying to understand things that are difficult to understand. Large-scale structure, in the end, is a feature of nonlinear and very, very messy astrophysics, and maybe it's not even fundamentally cosmological at some level, because the galaxies are the flotsam and jetsam that are moved around on an undulating ocean of dark matter that dominates by a factor of 6. And however, there has been substantial progress. You can be critiqued, dark matter can absolutely be critiqued as not having a fundamental causative agent identified, and the fact that a lot of the research is phenomenological in approach, but it's a very directed and theoretically motivated phenomenological coupling, because we can take galaxy redshift surveys such as the Sloan Digital Sky Survey, segregated out in color here to represent younger and older galaxies, showing that they cluster differently in the sky, and we can compare those to dark matter simulations and even venture prescriptions for how the baryons will follow the larger amount of dark matter in a cosmological simulation, and it checks out pretty well. I mean, we can explain what we see in the universe on these very large scales. These are scales of hundreds of millions of light years, billion light years, basically. What we're also doing, of course, is working back towards the Big Bang. We're talking about the expansion history of the universe. And as you probably know, our best tools for that sometimes occur in space. It's forgotten often that the Hubble Space Telescope would not get in a list of the world's 50 largest telescopes. It languishes around the 56th or 58th spot, which is amazing to people in the public who think it's the be-all and end-all. And it's probably full cost accounting, including the servicing missions. It's a $20 billion and counting mission. That's a big chunk of change for a 2-meter telescope. But of course, it's in an extraordinary environment. It's benefited from being rejuvenated by servicing missions, and it has a very excellent low background for doing deep observations of extended objects, galaxies. And so we've seen further out in the universe and back in cosmic time with the Hubble than with any other facility. And what we're trying to do here, of course, is work towards the beginning of the formation of baryonic clump material, stars and galaxies. And just as we've done the counting of galaxies almost to the limit we can, we've almost succeeded in the agenda of tracing back the star formation history of the universe. The goal of seeing first light will in fact not be left to the Hubble, which is essentially running out of steam at this point, trying to go deeper or fainter or higher redshift, but will be left to the James Webb Space Telescope, which we hope to be launched. That's an $8 billion and counting mission, hopefully launched in about 7 or 8 years. Remember that these are kind of slightly bizarre situations represented cartoonishly, because that's almost all you can do if you're not going to just use the math. That the universe is expanding, and the universe has had both a decelerating phase lasting about 8 billion years and an accelerating phase that's from 5 billion years ago to the present day and on into the infinite future, as far as we can tell. And so you're looking at photons at a redshift by expansion since the time of emission. At the highest redshifts we're able to observe roughly 8. You're talking about an object that was receding from where we would eventually be, because we hadn't formed yet, at 2.5 times the velocity of light. Subsequent deceleration allowed that photon to reach us, and the lower cartoon tries to represent this strange scramble where asymptotically as the photon eventually reaches us, having traveled roughly 43 billion light years, special local inertial frames indeed give the result that the photon arrives at 300,000 kilometers per second, as indeed it should and must and did. And this is representing an era when the universe was a very different place. So we're probing some very alien terrain here, alien in time and in space and physical conditions. As I mentioned, the properties of galaxies on mass were insufficient to carry out the agenda of tracing the expansion history of the universe. So in very skeletal form, I'll just indicate a couple of the ways we've tried to do better. Clearly, stellar cataclysms, which can, for a few days, rival the brightness of an entire galaxy and appear to be in certain categories like standard bombs, become a way to use a standard candle and trace the expansion history. So here we have, referencing Hubble's 1929 graph, what can be done with supernovae, and of course this was a decade ago. Taking it more to the present day, the supernovae as distance indicators have been used to pretty much discriminate between the available world models and home in on a situation where there was deceleration and now there's acceleration. So both the dark matter and the dark energy are components that you invoke to explain this expansion history. There are other ways to go maybe even further, not as mature science, because our understanding of the astrophysics of gamma ray bursts is not as mature, but it's very speculatively, Hubble diagrams have now been published out to redshift 6 or 7 using gamma ray bursts. And the gamma ray burst potentially could be a tracer or a probe, literally to the cusp of the formation of the first substantial bound structures in the universe. Very exciting. That's the sort of frontier of the subject, if you like. And if you're, not that we're so trivial and picky-unus to care about records or anything, but if you care about records, then here's how the redshift record has gone over the past time. There are, if you didn't know what these were, you could guess. Any astronomers in the room, of course, know, but you could guess. But basically, for a while, for a good 30 years, a redshift record were held by active galaxies, by quasars and AGN. That record was then recovered. Gravitational lensed galaxies, that's something that Richard Ellis knows a lot about, and hopefully we'll talk some about, were a tool for getting us really far and for beating out the AGN in terms of the highest redshifts. And the up-and-coming gamma ray burst, of course, held the record, which was then just recaptured by galaxies a year ago. So it's a bit of a battle royal at the high redshift end. It's a pissing contest for those that care about that kind of thing. We're way above that. We're far more mature. And what does this data look like? I'm going to wrap up now, just to show you a little of how horrible this data is, because we really end up with a problem. The history of astronomical spectroscopy of galaxies is conducted at optical wavelengths, but at a redshift of 8 or 9, the Lyman limit, the sort of hard cutoff to the light of the galaxy, is shifted almost entirely through your optical spectrum, and so you're reduced in these two examples of two of the very highest redshift objects with confirmed spectra. I'm not talking about photometric redshifts or any of that kind of stuff. I'll stick to pure spectroscopy here. These are near-infrared spectra, and they're pretty graphic. You can see what's going on, see whether you believe them yourself, but that's what you're doing. And you're back to the old days of Shiner with your multi-night observations here, just to get a single, pretty crappy spectrum. But that's what it takes at the limit. And why is it so hard? Well, I've already alluded to why it's so hard. By the time you move out to even redshift of 3 or 4, all the features you use to identify a galaxy and measure its redshift have shifted into the hideous regime of the OH bands. And you can see here, these are not scaled to each other, but you can see the OH bands in the optical, and then moving into the infrared, and then just the thermal background rising up to sort of whack you in the face as you hit 2 microns. And so here's the observing challenge, just to put it in a nutshell, because I'm nearly finished. So here's the sky background in terms of emissivity, because when, as you see in either of these physical examples, you're observing an extended object in the presence of background emission. And the terrestrial environment has air glow and lots of nasty things. Space environment is okay, but Hubble is actually in a low Earth orbit. It's not where you would choose to do spectroscopy. Dark side of the moon would be way better, but nobody has another $20 billion to throw at that right now. That's where I'd do spectroscopy if I had my druthers. So you're in a situation where the emissivity of the sky is a couple orders of magnitude higher as you now try and look for these very highest redshift galaxies. You just play this game out as far as you think you can play it. And if you just put a number on it, why is it a hard game? Because essentially, even with a 10-meter telescope, you're collecting 1 in 10 to the 54 of the photons that galaxy emitted. That's hard work. And if you work out what that means, it's about 50 photons a second coming into your telescope, which is dwarfed by 1,000 times more photons from the sky. And then you still have to, you're not making a little puddle of photons to detect the galaxy as an image. You're smearing them out into a spectrum and trying to detect features. That, my friends, is hard work. That's why it's fun, of course. You want to keep trying to do this. And so here I can summarize what this actually looks like, the bird's eye or photon's eye view. So we have an object that's moving 2.5 times the speed of light away from us. The photons overcome the galloping expansion. They come through on the Earth, and just hopefully they don't hit a cloud 2 miles up. And equally, we hope they don't just land uselessly beside the telescope. That stinks. That happens a lot too. And then they enter the miracles of modern technology, of fibers, of very efficient gratings and holographic gratings and spectrographs, and a spectrum that we hope tells us a little more about the limits of the universe. And that's where we are right now in the state of the art. And unlike other people, I'm going to resist any ritual Hubble bashing, and I will just end. Thank you.
Thank you very much. I guess there is someone who wants to have, yes, quite a few. I was expecting someone else who this morning didn't believe all that much in all these observations. But okay, so there was the lady at the back.
Oh, I'm sorry.
I'll ask an easy or straightforward question. We all believe that nothing goes faster than the speed of light. What do you mean when you say these things are moving away from us at 2 or 3 times the speed of light?
Oh, okay. Well, in sort of simple terms, the speed of light is an absolute limit as a function of special relativity. The cosmic expansion is governed by general relativity, which applies no speed limits. There's no speed limit in the theory for cosmic expansion. And in fact, in those early times, basically any galaxy, I think the boundaries of redshift 1.3, what is it, 1.3, I think, at which, at the time the light was emitted, any 2 points in the expanding metric were going at the speed of light.
Most things in the universe go faster than light. Think of the frame of reference, the rotating Earth. What do the stars do? They go around in circles. So anything that's more than a light year away, a light day away, it travels faster than light. In the circle it goes once a day. In fact, it can't go slower.
Yeah, see, cosmology is so liberating. You really need to get into this.
One question about what you passed around. Was that a focal plane plate that it provides the slits for the fiber optics?
Yes, and then there's re-imaging optics because your physical detector is the actual CCD is about this size, so you re-image.
Okay, and question number 2, I may have missed it, but in your wonderful slides about of all the surveys, I didn't see, or at least I didn't recognize my alma mater, the Smithsonian, and I'm wondering if you had included it.
Oh no, that was not a deliberate or even an accidental omission. I essentially bracketed a set of surveys. Let me think. I think I just basically took a decade window from the 2000 to 2010 for the modern era. I have a master list of these, of course, and there are others which have 100 or so. But you're right, the CFA was a pivotal survey of the 70s and 80s.
Yes?
Does the Hubble have any spectroscopic capability?
Yes, it does, and it's quite impressive. The Hubble has modest spectroscopic capabilities, mostly in the ultraviolet now, but it also has slitless spectroscopic capabilities with one of its imaging cameras, and at low resolution means you can go very faint with that because the sky backgrounds are so low. The trouble with the Hubble is the field of view are really small. So what astronomers have done on the ground, apart from eclipsing light gathering power of Hubble by a factor of 20 or 30 now, is that they've been able to create very fast telescopes with large focal planes and then tile those focal planes with really large cameras. And that's just something that we don't have any way to do in space right now, or really even in the near future.
Further question or remarks, comments? Yes?
What kind of precision is the intent with the higher redshifts in some degree larger
Yeah, the
uncertainty in Z's?
right. They're actually, some of them are trying to, you know, really harvest low precision redshifts. You won't call them photoz's, but that Primus survey that I included, that was an R of 200. Where I would say, you know, Deep 3, the telescope, Richard will talk about more of these surveys too. The typical survey has R of a few thousand. That's probably a more typical number. So it's certainly sufficient for, you know, a galaxy redshift, but you wouldn't call it precision redshift work at all.
What's the plus or minus Z typical redshift at around C is 3?
So it's just 1 over R, so it's like 0.2%.
2%.
0.2%.